An important distinction we have to make as chemists is between the empirical and molecular formulas, and so I want to talk a little bit about those today. So with an empirical formula, that's the simplest formula. It's the simplest whole number, smallest whole number ratios that we see in a chemical formula. And, this may sound weird without having something to compare that to, because it seems like that's all chemical formulas, right? That it's always the simplest whole number ratios that we put together. But the molecular formula is the chemical formula as it's written, but sometimes these things can have an empirical formula, meaning we can simplify things down. So let me give you a couple examples. Let's use some hydrocarbons as examples. So if we have C2H2, which is acetylene. So acetylene is used in torches, for example. That's one of the applications of it. C2H2, if I, can go to the simplest whole number ratio, a 2-to-2 ratio is a 1-to-1 ratio. So the empirical formula for acetylene would be CH. Now if I take C6H6, this is benzene. Benzene is a carcinogenic compound. It's got a ring structure. We'll talk a little bit about benzene a little bit later when we talk about organic solvents later in the year. Now, benzene is C6H6. If I was going to simplify this down to the simplest whole number ratio, it would also have the empirical formula of CH. Now let's take CH4. This is methane, which is the primary component in natural gas. Now I can't reduce down CH4 anymore, so the molecular formula is also the empirical formula. Right, I have a 1-to-4 ratio, so the simplest thing that divides into that, each of those is 1, so I have to keep it as 1-to-4. C2H6 is ethane. It's an alkane with 2 carbons in it, so it has the prefix eth. So C2H6, I can divide both of these by 2. That gives me a chemical formula of CH3 as an empirical formula. Okay, so empirical, simplest, broken down. This is not the way the compound actually looks, but I've reduced down the numbers in my molecular formula to their simplest ratio. Okay, so that's kind of what we're talking about when we're talking about empirical versus molecular formulas. So let's look at a couple examples of how this actually plays out with some compounds. So if I have a sample with a mass of 83.5 grams and it has 33.4 grams of sulfur and the rest is oxygen, then what is the empirical formula? So what I'm looking for is a compound with sulfur in it and oxygen in it. So I'm essentially looking to solve for my X and my Y. And the way that I can do this is using this information about the mass. Well, if I can go have grams of something and I'm trying to figure out a molar ratio of things, then the first step is going to be to convert these things to moles. So I have 33.4 grams of sulfur. Now I want to go from grams of sulfur to moles of sulfur. So in order to do that, I need to go to the periodic table, look up my molar mass of sulfur. For every 1 mole of sulfur, I have 32.07 grams. And from here, I see that I have 1.04 moles of sulfur in that many grams. Okay. Now, the rest of the mass of my compound is oxygen. So to find out how much oxygen I have in there, I need to take my total mass and subtract the mass of my sulfur. So when I take my 83.5 and subtract my 33.4, I end up with 50.10 or 50.1 grams of oxygen. Now I'm going to do the same operation here that I did with my sulfur. So I go to the periodic table and I check out my molar mass for my oxygen. It's 16 grams for every 1 mole of oxygen. And again, it's just the atomic mass from my periodic table here. And using this information then, and doing my math, I get 3.13 moles of oxygen. All right, well, now what do I do? Well, if I look at these ratios then, so if we're thinking about this by mass, and I'm looking for the simplest whole number ratio, then if I divide each of these by the lowest number of moles of each of these elements, then I should end up with a ratio here. So if I divide this guy by 1.04 by itself, then that will give me my 1. And then if I divide this guy by my 1.04, then this will give me how many of these guys I have with relation to this 1. And so when I do that math, it's about 3-ish. So if I do the math, it's actually out like this. But if I think about sig figs, then it's probably like 3.01, but I know it's simplest whole number ratios, so it's about a 1-to-3 ratio of my sulfur to oxygen. So if it's a 1-to-3 ratio, my simplest whole number ratios, my empirical formula here is going to be SO3. Okay, so the key to this is you need to figure out how many moles you have based on the masses that you have, and then you divide those numbers by the smallest in order to give you a 1, right? That's kind of your baseline. You're sort of normalizing all your data to that 1 and seeing how many of the others there are of that 1, and that will give you these whole number relationships. Okay, let's look at this from another standpoint. You can see here that I talked about this in terms of mass and mass composition. So if we talk about this in terms of percent composition, like with my benzoic acid here, if I know the percent composition by my elements, then I can also find its empirical formula. So the first thing that I need to do is I'm given that I have 68.8% of carbon, 5% of hydrogen, and 26.2% of oxygen by mass that make up a sample of benzoic acid. Now it doesn't tell you how much benzoic acid you had, so since we have percentages, the best first thing to do is to assume a 100-gram sample. And if you assume a 100-gram sample, then your percentages actually give you masses, because if I have a 100-gram sample total, then that means 68.8 grams of it are carbon. And it means that 5 grams of it are hydrogen, and 26.2%, or 26.2 grams then of my 100-gram sample are oxygen. So if I know the number of grams, then we do the same operation that we did with our sulfur and our oxygen. We need to convert to moles. Now in chemistry, when in doubt, you are probably going to be converting to moles if given grams, or just in general. It's actually a good rule of thumb. So when in doubt, convert to moles. So I'm going through and I'm finding my molar masses based on where things are in the periodic table. So I went and said, well, my mass of my carbon, and my mass of my hydrogen, the mass of my oxygen, and then using those I can figure out how many moles of each I have in a 100-gram sample given these mass percentages. So when I do that, I end up with 5.73 moles of carbon, 4.96 moles of hydrogen, and 1.64 moles of oxygen. Now I have 3 sig figs along the way for these, so I'm keeping and maintaining 3 significant figures for my number of moles here. Now what's my next step? If we think about what we did for the sulfur and the oxygen, I looked and I saw, well, which one is the smallest? I need to normalize all of these numbers to that one. So the smallest number here is my number of moles of oxygen. So if I divide my number of moles of oxygen here by my 1.64, that will give me my 1. If I divide my moles of hydrogen by 1.64, then that gives me this, 3.02. And if I multiply, or if I divide my moles of carbon by 1.64, again, we're normalizing all the way down here, then we get 3.5. Now, when I look at these, this gives me a 3.5 to 3 to 1 ratio. And you'll note that I didn't round the 3.5. I rounded this guy down because it's pretty dang close. If we look at a hundredths place, then we can probably assume that that rounds down. If I'm looking at a tenths place, then I'm going to have to use some judgment there. So I'm going to leave it as a 3.5. But we know that we have to have whole numbers here. So how do I get all of these to the lowest whole numbers that I need? Well, I need to multiply all of these by 2. And when I multiply all these by 2, that gives me a 7:6:2 ratio. And that's the lowest whole number ratio. And again, if we're thinking about empirical formulas, I can't divide all 3 of these by the same number to reduce it down further. So that means that my empirical formula will be C7H6O2. And that is the chemical formula, the empirical formula for my benzoic acid, that simplest whole number ratio. Okay, so that was using percent composition, but doing that same operation with our empirical formulas, normalizing the data to our 1, figuring out how many times we had by mass of each of our other components. Now let's relate that to the molecular formula. If we go back to our first example with the sulfur and the oxygen, we calculated an empirical formula of SO3. But what if I told you then that the actual mass of the compound is 160.14 grams per mole? So what is the molecular formula? Well, the molecular formula could be the empirical formula. We saw that with our methane example at the beginning, right? CH4, the simplest way we can reduce that down is still CH4. So we need to figure out if that's the simplest whole number ratio or not. So if we're trying to figure out the relationship between the molecular mass versus the mass of the empirical formula, however many times that mass of empirical formula that gives me my molecular mass will tell me how much I need to scale up my empirical formula. So by how many times do I have to multiply my empirical formula in order to get it to the molecular formula? And the way that we do that is this is sort of the math behind it, but I think it's pretty intuitive once we put some numbers to it. Now you'll see that the things that are missing here is this n value, but I can find that n value if I know that mass of the empirical formula. So I need to start there. So I have SO3. So I need to have the mass of sulfur plus 3 oxygens, and that'll give me my mass total. So sulfur is 32.07. And then if I have 3 times my oxygen, that's my 16. Then my empirical formula mass is 80.07. And I can keep that in AMU. I could put that into grams per mole. They're both the same thing. It's just whether or not I'm talking about one of these or 1 mole of those. So when I look at this, I say, well, this is the mass of my empirical formula, but I told you that the mass of the actual compound is this guy up here. So we know that this empirical formula is not my molecular formula because the molecular formula has a larger mass than this. So now I say, well, by how much, by how many times is that mass from my empirical formula? So that n value is going to be this 160.14 divided by my 80.07, and you can probably do that math in your head to see that that's 2. So that n value is how many times I need to multiply this whole chemical formula. So that means that my molecular formula is S2O6, 2 times the empirical formula. And I figured that out because I was given, or I measured, or I found in some way, shape, or form the molecular mass of this thing, the molar mass or the molecular mass. Again, whether or not we're talking about 1 or 1 mole of those things. So that's the relationship between empirical formulas and molecular formulas. It's kind of a subtle difference, but it's an important thing to note, especially as we get into multiple combinations of things and these different simple whole number ratios that can make new and interesting and unique compounds. So if you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.